Welcome back to lecture 13.2, where we are going to begin our discussion of the second law of thermodynamics. Okay. So to do this, we're actually going to imagine looking at our PV diagrams. And imagining some arbitrary set of processes where I start at some state A, I'm going to go to some state B, C, D, for example. And if I took some complicated path, what do we know about the closed loop? Okay, that's what I'm curious about. Where we go from A, say to B, to C, to D, and back to A. Well, what do we know about this system? Well, one thing we know is that since U, the internal energy, right? So when in doubt, remember we always think about these diagrams in terms of the first law, right? So let's start at the first law. du equals dq plus dw. So let's just think about these terms one at a time. So what do we know about du during this? Well, we know that since u is a state function, it only depends on where I'm at. So that in this process, when we go around the whole loop, that du is equal to 0. Right? We're unchanged. But this was equal to the integral of dq plus the integral of dw. So what that means is that if we were to say q loop is equal to minus the work done in the loop. Or the work done in the loop is equal to minus heat in the loop. And this one in particular, I want to inspect. Is this possible? That is it possible for the work in a loop to be minus the q in the loop? That is, if I had some net heat, right? So can I do something? Can I convert all heat in loop to work? Well, before we answer that question, let's answer the other one. Okay? Can I convert all work in loop to heat? All right, this one. Well, for sure we can do this one, right? That's basically, imagine back to the experiment of Joule, right? Where you had these paddles inside of water, and you do some work by spinning this thing around. You put some work into it and the temperature went up, you converted all of your work irreversibly towards all of your work irreversibly to heat. You can also imagine doing this with, say, a battery, right? We talked about the work done by a battery. You could have a battery with doing some work, having some current flow through a resistor, have all that resistor dump its heat into a vessel, right? So you had some battery, and it dumps all of its heat into some resistor inside your system. So we're happy with that. But is that the same as converting all the heat to work? Well, we already have a clue. We realized that this one was irreversible, right? The answer to this one is so different, in fact, that it defines, so this one is different, and it's so different it defines the second law. So the book actually has two nice definitions, or two statements of the second law of thermodynamics. So this is section 4.3 in your book. Okay, so let's write the Kelvin statement of the second law, paraphrased, of course. A transformation whose only final result is to transform into work heat extracted from a source which is at the same temperature throughout is impossible. Okay, so that's the Kelvin statement of the second law. So let's parse this. So there's two key things. One of which is the only, right? That is the only final result being work. So here we're saying we're going to do something using some heat, and we can't only extract work, right? So this one is not possible because you're having to put heat in, for example, but it's transforming into work only. So you got to have something besides work being produced, and we'll see what that is. And the other thing is the A source, or really a single source. That is, we're going to have at least two sources of heat, right? We're going to need at least two. So can't only produce work and need at least two temperatures. Okay, so there's a second and what we will prove is equivalent form or statement of the second law. And this one is done by Clausius. So let's write down the Clausius statement of second law. So the Clausius statement of the second law is a transformation whose only final result is to transfer heat from a body at a given temperature to a body at a higher temperature is impossible. Okay. That is, if the only final result is to transfer heat from a body at a lower temperature to a higher temperature is impossible. Well, that makes sense. We already know that heat flows from hot to cold spontaneously. Right? So to get it to flow from cold to hot, we're also going to have to do something else. We're going to have to add some work. Okay? So that's another statement of the second law. So to dive into this deeper, we're going to actually explore the Carnot cycle in the next section.